Hi everyone, this video covers the second part of our mini packet on semi-log plots. Alright, so I'm just going to jump into the examples using raw data. The table below shows, the table below gives values for the function f of x at selected values of t. And here we go. Graph the data on the semi-log plot and label your axes. So here is the graph. Ignore the pink stuff for now, that comes at a later part of the problem. So I've graphed all the points given. Again, ignore the pink stuff, that is later in the problem. I'll explain that in a moment. Alright, and then it says, what does this graph say about the data? This graph appears to be linear on a semi-log plot. If it's linear on a semi-log plot, the data must be exponential. Okay? Because a semi-log plot, exponential and logs are inverses of each other. Alright, approximate the values of f of 3 and f of 9 using the graph. Alright, I decided to make a regression equation, but you could have also used the graph and kind of estimated, since that's what it instructs you to do. It's more exact with a regression model. So what I did was I found the regression model, and then I plugged in 3 and plugged in 9, and I got these values. Now, you could also linearize, like find the linear equation, and then plug in 3 and 9, and that would also be a legitimate approximation for this problem. All right. Linearization of bacteria population. Okay, make a scatter plot with the data. What does the shape of the plot suggest about a regression model to fit the data set? Okay, so we did a very similar problem to this one already. In this case, they don't give us an equation. So in this case, we are stuck with the values we're given. Let me go through this. So stat, edit, we've got 0, 1, 2, 3, 4. Bacteria in the thousands, we've got 6.24, 15.98, 42.54, 114.65, 310.67. Check. Okay, and let me turn my stat plot on. So if you wanted to see this graph, here's what it looks like to start. Clearly it is exponential, okay, which makes sense because we're doing semi-log plots. All right, then they're using natural log, which would indicate that the exponential function uses e. So going back to my chart, I'm going to highlight L3, hit enter, and do natural log of L2. And then this is what I got. And I gave 4 decimal places, but I think if it's not specified, 3 is fine. All right, it appears to be exponential. To linearize the data, complete the table at the right. There we did. Graph the linearized data and find a linear regression equation where this is, I'm going to call this y with a hat, or y prime. See the image below. Our graph looks like their graph, so we're good. If you find the linear equation, this is how you do that. Go back to stat. Now we're going to go to linear, which is 4. But in this case, you need to make sure you change this to L3. And we can vars, y vars if you want to graph it also. Please remember that if you do that, you would also want to change your scatter plot. Oops, sorry. You would also want to change your scatter plot, otherwise you're going to have an exponential scatter plot and a linear regression model. There we go, and that's how I got this here. And you could also graph it if you want to see it. So 9, there we go. Okay, use the regression model for the linearized data to find a model for the original data set. Okay, so what you're doing now is, again, we weren't given the original formula, but now we have a linear formula. So we're going to work backwards to try to figure out what the original exponential function was. So we're going to do e to both sides to cancel out the natural log. This gives us y equals e to the blah, 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 times e to the this number. This is approximately this decimal. I did not know that off the top of my head. I did use a calculator. Rounded to 3 decimal places, this is what I got. Now, I kept this here because there is another part where they ask us to plug in a number, and you want to be as exact as possible. So here, when it says use the equation that models the original data to predict the number of bacteria present after 12 hours, I used this equation with more decimal places and plugged in 12. And I got this value. So the answer is after 12 hours, bacteria population is approximately this, and I made sure to add 1,000 because that column is dealing in thousands. All right. Baseball superstars. Create a semi-log plot for this data and interpret the plot using, again, we're using log, but this time common log. Okay. So here is our years. Here are the salaries in millions. This is what I plugged into the scatter plot rather than 1980, 1982. So what I did was I just decided, I just didn't decide. It was specified. For 1980, use t equals 0, find an exponential regression model for the data. So that's what I did. I won't do this again because this part is very similar to what we just did. You're just using an exponential regression model instead of linear. If this is something you're still kind of having trouble with, let me know. I'm happy to go over it with you outside of class. And this is the rounded version. Final linearization, we're going to use common log. So this is what we have. And remember, because I'm working with this, I used all my decimal places. I took log of both sides. This is added. The x comes down in front. Here we go. Explain the meaning of the slope and the y-intercept. Now, I actually didn't like this question because it's difficult to explain the slope and the y-intercept of a linear representation of an exponential function. I think this is what they were looking for here. It says, I wrote the slope represents the annual percentage increase in superstar salaries. So it's not the increase, it's like the percentage. It's mapping out big increases because we already know it's increasing at an exponential rate. The y-intercept, because 0 is 1980, this corresponds to the predicted superstar salary in 1980, which actually doesn't exactly match what was given, but that's why it's a model and not exact. What is the predicted superstar salary for a player in 2010? Well, we plugged in 30, we plugged it into our exponential function, and we got this. So replace this and solve for y. So here we're using our linear equation instead, and we got the same thing. That is not always the case. You'll notice that sometimes it's slightly off, but it should be very, very similar if you did everything right. All right, so, oops, what's going on here? I will include this in my email also, but I am reducing the homework that I had intended to give you guys. Go ahead and cross this part out. And I do have some answers, so I'm going to hide that. There are 3, let's see here, 3, 4, 5 is on this page. Or 3, 4, 5, 6, 7 and 8, 9, and 10. Please cross this out as well. Okay, so this homework, because I was absent, I'm making all of this optional. This is worth something for team points. So if your team would like to go for the 1% extra credit on your final exam, I encourage you to do this. But if you have a lot of other stuff going on and you don't get to it, it does not count for your grade. It just counts for team points. Okay, so Please copy this down if you have a moment. Do all the homework aside from what's crossed out. I will include the numbers in my email, and if you have questions, please let me know. Thank you so much.